We're very happy to have Jonathan Libgober today. So some of you know Jonathan. He was visiting several Australian universities when he was on the job market. So Jonathan was from Harvard. He spent some time at Columbia and is now assistant professor at the USC. Jonathan is a very creative theorist. So he has published in AJ Micro, and his job market paper is currently R&R at Restart. So today he's going to tell us something about machine learning for strategic influence. So you have 75 minutes, 1 hour presentation plus some time for Q&A.
Yeah, thanks so much for the invitation. The visit to Australia was certainly a highlight of the job market, and I'm just glad I'm able to stay in touch with everyone. I was very fortunate to be able to work on this project with Inku Cho, who I believe is in the audience, and it's just been a really wonderful working with him. And this paper is part of what I would say is a nascent literature studying how machine learning algorithms may perform in theoretical models. And we think this is an important issue because if you think about it, algorithms are really increasingly being used either explicitly or implicitly as a way of guiding economic behavior. So as an example, from my own life, I was recently trying to buy a mask for obvious reasons. And I know nothing about making masks. A friend recommended I go to this website called Etsy, which is a platform for arts and craft sellers. And if you go to this website, you search masks, and you get a bunch of outcomes, possibilities. Typically, the top is sort of the most prominent, and there might be other markings about it. And so, typically the ones at the top are the ones that people just go with. And if you look, it's sorted by what they call relevancy. And so you might wonder what that is. And what it means is that there's an algorithm in the background. Okay, so they're very cagey about what this algorithm actually is. So I can't really tell you what Etsy is doing. But what I can tell you is that relevancy is not just, it's not like a linguistic thing. It's actually aggregating past experiences and using them to give, recommendations to buyers. Okay, so I go on this website. I don't know anything about masks. I just pick the first thing I see. So the question that we're interested in this paper is whether I, as someone who just does what the algorithm says, am acting in a rational way. Okay, so the question we're interested in, and I don't want to own Etsy too much. I think we are admittedly interested in a more abstract question. But the question is whether algorithms can induce behavior that is what we should call as if rational. And we'll be interested in the question theorists are always interested in, namely if it can, when, how, and how well. You might wonder, what do I mean by rationality? It does mean a lot of things. In this presentation, we will be interested mostly on the inference question. So what do I mean by that? Well, if we think about what a rational player would do in a kind of buyer-seller game, they would be able to look at the price and then make an inference about what that price means about their value for the product. So what does this look like? So we should be pretty familiar with this. It's pretty standard. The first step is to figure out what the strategy a seller would be using. So how does quality map into price? Then you look at the realized choices. So I see the price, for instance. Using those two, we have everything we need to do Bayes' rule. And then we update our beliefs, we form a conditional expectation, and then we buy or not buy. Okay? And so what we're interested in is whether an algorithm can get something like this. And just to give away where I'm going, we have an algorithm which is going to get close to rationality, and we'll be interested in the sense in which it can get close. But I would say, I think our contribution is really in formalizing this problem in a way that lets diverse literatures talk to one another. Now, the question of, how do we figure out whether it makes sense for a buyer to buy or not, it's really, if you think about it, that's not too different from a kind of standard econometric or machine learning exercise, okay? Because, what that exercise would look like is taking some set of models, and where by model I mean mapping from observables into, recommendation action. And so then you would just, have to fit some model. The difference with our exercise is that we're interested in this aspect where this data generating process might be endogenous. Okay, so whether what data generating process you're going to see, specifically, what sequence of prices you're going to see, is going to be endogenous to the algorithm, right? In particular, whether or not this algorithm is able to achieve a rational reply. Okay, so that's sort of an element that's missing from the usual predict education on earnings exercise. But I think it's very realistic in these kinds of applications we're looking at. Sellers really do think what this algorithm is doing and how it influences their strategy. I want to emphasize 3 aspects of our exercise which are going to make it non-trivial. The first is that we want this algorithm to be as parameter free as possible, which is going to mean that we want the algorithm to, not just look at the parameters of the environment and then tell the buyer whether they should, what the rational rule is. Okay, it's going to have to come from, the data and the observables. The second is we're going to be focused on cases where, in fact, there is this incentive to manipulate any limited cognitive ability of the algorithm. Okay, so we're going to be looking at a setting where if, in fact, it wasn't possible to get to rationality, then that would be something the seller could exploit. Shouldn't be too surprising that that can happen, but it's going to be a very important feature in our environment, and I'll walk through exactly how that works. And the last is that what we want to take as given is a set of models that can be fit to the data. Remember, by model, I mean mapping from observables into recommendation. Our assumption is going to be that there's a limit on the set of models that can be fit, but we're going to allow for creativity and flexibility on other dimensions, okay? So what this is really pointing to is what I think is an interesting trade-off that our analysis is trying to highlight, which is a tension between having rich models and rich sets of models and coarse sets of models. So what do I mean by that? Well, you might think that I don't, maybe I, put lots and lots of models into my algorithm, and as a result, I can fit lots and lots of data. Okay, we're going to show that in our environment, that would give you something intractable, and it wouldn't necessarily, and it wouldn't, you wouldn't be able to have enough data to figure out, to ensure rational replies. Okay, but on the other hand, if you were to use a limited set of models, then that's something, as I mentioned, is the seller is going to be able to exploit. Okay, so there's going to be a trade-off between rich models, which are going to have better behavioral properties, still not perfect, but better behavioral properties, but worse statistical properties, versus coarse models, which have worse behavioral properties, but better statistical properties. So the game we're going to look at is going to be combining 2 elements. The first is what we'll call a machine game, which is the game between the algorithm designer and the seller in our model, as well as a stage game, which is going to be the particular interaction between the buyer and the seller. Okay, so I want you to think machine game is, Etsy algorithm, seller. The stage game is seller, and stream of buyers like me. So the particular algorithm we're going to look at is called the adaptive boosting algorithm. It's very widely used in machine learning applications. It's going to be nice for us because it's going to allow us to reduce this rationality condition to something much simpler, and in particular one where we're able to kind of show how quickly we're going to be able to estimate the underlying parameters. So in terms of takeaways I want you to leave with today, I would say there's two. The first is if you look at how this algorithm works, what it does is it fits a model to the data, to some distribution, I should say. It fits the model to some distribution, okay, to some data, and then it fits it again, and then it tries fitting it repeatedly, and it changes the way that it fits, the way it's fitting these models to the data at each step, okay? And that's taking into consideration this kind of limited computational ability in that you can only fit certain models to the data. And so the way it's going to work is it's going to be combining these decision rules. So in that sense, what we're emphasizing is that this ability to combine decision rules rather than fit exotic decision rules is really a key to rationality and a way that you can induce rational behavior. And the second, and I don't think this is a super deep point if you look at it, but I think is maybe more provocative, is in our case, as I said, this problem is intractable if we don't think about the incentives of the seller. And that means that kind of doing this endogenizing things, looking at the, making this data generating process endogenous actually makes our lives easier because it says we only need to worry about, particular distributions. And so I think that's the kind of, typically I think we're used to thinking endogeneity makes things harder. In our case, it makes things easier. Cool. I see the chat is empty, so I will keep going. Overview, it's pretty simple. I have a model, I have results. There's going to be a literature review in the middle. So the model we're looking at, it's going to start with a long-lived rational agent, as well as a sequence of short-lived agents. Okay, and so rational agent is going to be the seller. The short-lived agents are going to be the buyers. So I'm first going to tell you about this buyer-seller interaction and how we're modeling it. And then I'm going to tell you about this algorithm-seller interaction. And I'll try to keep these as separate as I can, although I'll have to reference the algorithm at some point. And then the last thing I want to say is that in this game, there's going to be two forms of uncertainty. There's going to be persistent uncertainty, which is going to be fixed throughout the interaction. So you can think of that as seller quality, for instance. And then there's going to be idiosyncratic states, which are going to be redrawn IID at every period. So you can think about that as product quality, for instance. The probability that the mask that's being sold in that period is of high quality. So we're going to have the rational actor choose a strategy at time 1, okay? So they're going to choose it with commitment, and so it's going to be fixed throughout the interaction. And the pricing strategy is going to be a mapping from states into distribution over prices, which you can take to be positive reals. I should have said that. And in fact, in principle, I don't want to restrict too much, so I'll let, if the seller wants to randomize over these pricing strategies, they can. Okay. So, but because so depending on what the distribution is, there might be different information about the underlying state revealed by the price. Okay. So the rational actor moves at time 1, and a buyer arrives at every integer greater than 1. Okay. And immediately before the buyer arrives, all of the parameters of the problem are going to be realized. So that means first, if the seller is randomizing over the pricing strategy, then that has to be realized, the particular pricing strategy in that period. Then we're going to have a state, realized as well. And these two together are going to give a distribution over prices. Good. And so then that'll be all the parameters that a buyer would need to make a decision. They're going to arrive at time 2. They're going to they have to decide whether they want to buy or not. That can depend on, that's going to be determined by an algorithm that's going to be decided upon at some earlier stage. And together with the realized strategy and the realized price, that's going to determine the move that the buyer is going to make. Okay, good. So there's going to be a decision, and afterwards, we're going to have something added to the data set, which the algorithm can use at later stages. So, in particular, it's going to include the price, the strategy, and we're also going to assume that the algorithm observes the highest payoff action. So in particular, we'll know whether, given the price, we'll know whether buying or not buying would have given the buyer a higher payoff. This is to avoid certain selection issues that might arise. And you could also get it in.
Jonathan, can I intersect to ask a clarifying question?
Yes.
So when the buyer arrives, the state has been drawn, and the price also has been drawn, but the buyer only observes the price. Is that correct? Or he also observes the state?
He does not observe the state.
Okay, and what's the role of the algorithm then? So it's a recommendation as of whether to buy or not, or
Yeah, that's right. The algorithm is going to, look at the data, which is strategies, prices, and ex post the state's observable. Okay, you can think of that, and it'll use that to kind of inform buyers at later stages what to buy and what to do.
Okay, thanks.
Also,
Good.
clarifying question, Alex,
Yes.
here regarding how do you add the observations to the data set? So clearly I can really prefer something if I chose to purchase it, but if not, how is that added to the data set or not? I think I'm a little bit confused about what's going on.
This question of how would I observe it if I didn't I didn't buy, how would I observe the quality?
How do you observe it, or how do you decide to add it or throw it away?
Yeah, so we're not, it's just, it's an assumption for us. If you thought that there were like many buyers, then maybe the seller, if they really needed to figure out what the quality was, they could do some kind of, they could give a recommendation to one buyer and have them figure out the quality. I don't, there's not I don't have for the model, it's just an assumption that it's ex post observable.
Okay.
But I think there's lots of, there's lots of ways you could embellish it to get that as a possibility, I think. Good. So that everything time 1.66 to 2.33 is going to be the stage game. I'm going to tell you about the payoffs we'll look at in a second. But notice that, observations are going to be conditionally IID, and that's important. Okay. So I already said a little bit about this game. So the second component is the machine game, which is the interaction between the algorithm and the seller. And so the algorithm is going to be chosen at time -1 before anything happens. And importantly, the persistent uncertainty that I mentioned earlier is going to be realized after the algorithm is chosen. Okay, so we're going to want this algorithm to work well, for a variety of, for many possible parameters of the persistent uncertainty, which is this first difficulty I mentioned earlier. Okay, and then as I said, the rational actor moves afterwards, after this persistent uncertainty. So in particular, the rational actor, when they move, they're going to know this persistent uncertainty, but the algorithm is not. Capturing that, Etsy wants their algorithm to work for masks and for mugs and for lots of different products. Okay, so machine game is algorithm parameter strategy that determines what happens in the stage game. And so the assumption is what's observed is the price, the strategy, if there's randomization, as well as the ex post, which action gives the higher ex post payoff. Okay, so now let me say a little bit about what this algorithm is. So our assumption is that there's some computer code that we can write which solves problems of the following form. Okay, so to kind of understand what this objective is, notice that if if we had a model H that could fit exactly, could match 1 or -1, okay, then then this objective would just be a sum of a bunch of 1s. And so then this whole objective would be equal to 1, okay? If you got everything wrong, then all of these terms would be -1, and then this objective would be -1. If you were wrong with probably 1/2, then this would be 0. Okay, so kind of how close to 1 measures how good the fit is. Okay, and so the script H is called a hypothesis class, and our assumption is that this is specified and fixed in advance. Okay, and so you can imagine if I'm adding more and more H's, that I'm going to do better and better here. But one of the things we're highlighting is this trade-off in the richness of H. So to say a little bit about these limitations, a kind of a typical machine learning problem, is to look at an image and to classify it as either a dog or a cat, for instance. And so if you're given a 28 by 28 image, right, then that's like, the image is kind of like an observable, and whether or not it's a dog or a cat is this label Y, right? Okay, and so the set of all possible models that you would need to fit any possible picture is 10 to the 236, which for reference is, orders and orders of magnitude larger than atoms in the universe. Okay, so we have, this is our interpretation of kind of limiting the size in the of this hypothesis class. But we'll allow for other forms of processing. So this is the constraint in the models that can be fit to data. As I said, our algorithm is going to run this multiple times and then combine the rules in a particular ways. And we're also going to allow for the input prices to be massaged in a certain way. Okay. And so the algorithm designer is choosing this. Okay, so let me say a little bit about the payoffs. So, in what I'm going to write and describe, I'm going to take the state to be binary. That's not super important. But the buyer is going to want to use the rational rule, which would have them buy whenever the expected value, conditional on the strategy and the price, is larger than 0. Okay? So that's kind of the rule that we're trying to, to get this algorithm to output, but across a variety of these environments. Now, what's the seller trying to do? So our assumption is that the seller is going to have a profit function, which is depends on the price the state, I mean, both, sources of uncertainty, as well as the buyer's decision. So, exactly why the assumptions I'm about to show you are important. I think I'll come back to that later. I think it's maybe slightly hard to appreciate right now. But what I want to say is that the seller's profit is not simply, price minus cost. You can imagine maybe there's some outside market in the background, so the Etsy seller has to choose the same price online as in the store. Okay, and so maybe the profit they get, from a buyer buying online is not, if I don't buy the mask online, the seller's profit is not, zero. If no one buys the mask online, the seller's profit is not necessarily zero. So the assumptions that we need, which are going to generate the incentive to exploit the algorithm, are here. I admit this is a lot to look at, but I want to emphasize the part of it that's really important, which is the second line, which says that when the state is high, when this is a high quality mask, the seller would like the buyer to not buy, would like this algorithm to not buy, to not recommend purchasing, and in particular charge a high price. So what the algorithm, so what the seller would like to do is charge a high price, slightly below the value for the product, but have the buyer not buy, okay? So in particular, this is gonna be the action which, given a rational buyer, the seller couldn't get. So, this set of assumptions are borrowed from this paper of Rubinstein, and it's written slightly differently. So, if you go and look, it is not 100% mapping. But I'm, for expositional reasons, I'm kind of doing things slightly differently. But what he shows is that if it were possible to induce a rational reply, then because of this second bullet point, where this loss is very, very large, the seller wouldn't sell in the high state. So there would be this unraveling that happens when the product is high. And I'll show you later that if there's a limitation, then that's something that the seller could exploit. So I also don't want to spend too much time on this, but one thing you might recognize is that if there's a lot of randomness in the environment, so there's going to be uncertainty in the output of the algorithm, right? So the criterion we use to say this algorithm works well is that it ensures that the outcome is giving me the correct recommendation with high probability. So what does that mean? So, you can imagine, I'm going to have lots of data generated. Okay, and so there's going to be uncertainty in the thing I'm left with, right? So the criterion says that with probability 1 minus delta, the thing that you're left with is going to make an error with probability epsilon, okay? And where, and what I get to pick is the amount of, if I've given enough data, then I can ensure that these two probabilities are appropriately small, okay? And so the algorithm is going to produce a classifier, by which I mean it's going to give a prediction -1 or 1 for every possible observation. Okay, so I have a question in the chat. So the price and the strategy are going to give information potentially about the underlying parameter. Okay, so that's the source of information generation in the model. I mean, of course, it's going to come from, no one's updating beliefs, right? But that's kind of the information that's being used. So yeah, you can think price, strategy, and then ex post state is the data set. And then yeah. Okay, so hopefully that answers the clarifying question. Good. So probably refers to this probability of producing the classifier, and approximately is the probability of making the right prediction. So our assumption is that the seller is going to try to maximize their undiscounted payoffs. What that means is that, you know, any kind of short-lived gains to exploitation are not going to matter for the seller. They're only going to want to use long-run gains. So we talk about, you know, we can relax it a little bit. There's some the results, the statement of the results. You have to be a little bit careful, but we can handle discounting, and we talk about it in the paper. So just to review our goal, it's to design an algorithm which achieves rational replies for the agents. By achieve, we mean this, you know, PAC-Learnability criterion. We're going to take it as given a constraint on script H. So there's going to be a constraint on the models that can be fit to the data. And we're not going to allow, and in particular, because this persistent uncertainty is realized after the algorithm is chosen, you know, the algorithm can't depend on this persistent uncertainty. Okay, let me say a little bit about the literature. So I think there's, you know, two literatures I want to highlight that some of you may be familiar with. The first is this literature on economic agents as statisticians. So there's a long tradition in econ of thinking about, you know, economic behavior as a result of statistical algorithms. I think going back to the 80s, Annie's paper does this in games. I think, so our difference is, I would say there's two defining features. So the first is that our game features this strategic inference issue of having to, you know, infer something, you know, you looking at the price and making an inference about the underlying state, as well as the fact that we're really interested in this construction of algorithms. So in the sense that we allow for kind of new models, if you'd like to be fit, to be kind of constructed, taking as given the constraint of what can be fit. So that I think, you know, the fact that models are endogenous in our setting, because it kind of depends on, you know, how many times you try to fit a model to the data, that's sort of something that distinguishes our exercise. Okay, and so the second thing I want to say is that we're also related to this literature on model misspecification. So if you think about it, having a restricted set of models is a lot like being misspecified, okay? Because, you know, you're not able to take the optimal action given the parameters. You're kind of restricted in what you can and what you can fit. And a lot of these departures, you know, people have been looking at from rationality can be understood as a form of model misspecification. Now, what's interesting about our exercise is that how misspecified you are is again going to be endogenous, right? Because the more times you try to fit this, you know, a model to the data, you know, depending on how you construct the algorithm, you're going to be more or less misspecified endogenously. Okay, and so that's, I think, perhaps not an obvious connection, but I think an important one. And the last thing is there's this, the algorithm that we use, it was first, you know, introduced by Freund and Shapiri. There have been many, many modifications of it. It's pretty well studied. Some of them are helpful for extensions of what we do. Okay, so any questions? Okay, great. Good. So the first thing I want to say is about this impossibility result I alluded to earlier. So if you think about it, we're allowing the seller to, randomize, over pricing strategies potentially, and also over, realized prices. The set of possible observations that you could be looking at is very, very large. Okay, so you could be seeing, there's lots of different possible prices, lots of different possible strategies, and so you're going to have to make a prediction for a lot of them, for all of them, and there's just too many. Okay, so and so the first result is that this exercise is not going to be possible unless we restrict the set of strategies in some way. Okay. Now, if you kind of made everything very finite, then, in principle, this result would hold. But, as we'll see, that kind of restriction is exactly what the seller is going to try to exploit. So technically, what, in the paper, we talk about, VC dimension as a way of articulating this more formally. In fact, it's very dramatic if you kind of allow this failure is very dramatic in the case where you allow the seller to randomize over the pricing strategy. But I think in terms of intuition, it's just there's too much to predict. I think that's sort of the thing I want to highlight. Okay, so now I want to get to more about the particular algorithm we're going to use. And in order to do that, I'm first going to need to tell you about this script H we're going to take as given. So the set of script H we're going to look at is a set of single threshold classifiers. What that means is we're going to assume that the buyer, that if the buyer uses a classifier in script H, then they have to make the same decision whether or not the price is on a given side of some fixed threshold. Okay? So, in other words, buy if the price is above this threshold, don't buy if it's below, or vice versa. And also, I'll note here that I'm now dropping the dependence on sigma, and that's intentional. Okay, so the algorithm that we're going to look at isn't going to use sigma, although the fact that we don't get into trouble is something that is going to something that depends on the seller's payoff. So the algorithm we're going to construct is going to take H's that emerge from fitting models to the data, and looking at a convex combination of them, and having the buyer purchase whenever this convex combination is greater than or equal to 0. So in this algorithm, I need to tell you what these weights are. So, that's sort of the heart of the algorithm, is actually constructing these weights. But the important point, which I've been emphasizing, is that all you're going to fit at any given stage are these H functions, which are mappings from prices into 1 or -1. I'll also say that when we run the algorithm, we need to do some massaging of the prices. I think it's maybe clearer if I tell you, about where that comes up in the proof. But first, I want to tell you where the what's going on with the single threshold classifiers, and then I'll tell you explicitly what the algorithm is.
Hi, Johnson.
Yeah.
Hi. So a quick question. You mentioned several times that you require the price to be massaged, but I have no idea what you mean by massaging the price. What do you mean by that?
So what we mean is that the input of the algorithm is not going to be the realized price, but it's going to be something slightly different. So the algorithm's not going to take the price as given, but it's going to take something slightly different as given and fit that to the data.
All right.
And there's various options you could follow here.
Okay, it's like a perturbation of the ordinal prices.
That's right. That's right. That's right.
Okay.
That's right. Thank you for. You're right. It's a little hand wavy.
Jonathan, I also have a question. So when you say we need to specify the weights and then, but the algorithm only fits the H functions.
Yeah.
So how should I understand that? So you assume weights given by someone, presumably the seller.
I will tell you the alphas that we use.
Okay.
So I'm going to do it. The H's come from solving this optimization problem.
I see.
But I have to also, so it's not enough. So this, and I really wish I had a whiteboard, but so, the optimization problem that I wrote down had a distribution over prices. And so when we run the algorithm, we'll also be changing what distribution we use.
Right.
But so it'll be a slightly different optimization problem at each step. But the point is, each time we're only solving an optimization problem of that form.
Mm-hmm. Yeah.
And then I'm going to tell you what the weights are. And then you're going to put them together in this way. And then that's the recommendation is buy above the threshold and don't buy.
Okay.
Buy when it's positive and don't buy when it's negative.
Okay.
Good, thanks. Okay, so good. So first I want to say a little bit about the single threshold classifiers. In particular, I want to, so first of all, I think it's a very natural class to look at, because if we didn't have this inference problem, we looked at this particular environment, then the buyer's optimal rule would in fact have this threshold form, right? Because, and so in order to find the rational reply of the buyer, given a sigma, all we would need to do is keep track of the lowest price at which the buyer didn't want to buy, and then the highest price at which the buyer did want to buy, and then have the buyer make, just put the threshold in the middle, and then tell the buyer, buy whenever the price is below the threshold, don't buy whenever the price is above the threshold. Okay, so, without inference, single threshold classifiers, do very well. And this works due to the fact that we have monotone best replies. The problem with what happens with inference is that we might get something non-monotone. And here's where the assumptions I had on the seller's profit are going to play a role. So we could be in a situation where with state dependence, the rational rule would be non-monotone, in the sense that it would have the buyer want to buy at the extremes, but not buy in the middle. Okay, so why would the seller do this? Well, remember, what the seller wants the buyer to do is not buy at a high price. So the seller wants to charge a high price when the state is H, but they don't want the buyer to buy. Okay, so that's kind of where all of this assumption on the preferences are playing a role, where this incentive to exploit comes from. Okay, so what that means is if the seller uses this non-monotone rule, what they can do is force a buyer that was restricted to using single threshold classifiers to make a mistake, right? Because if a buyer is only fitting single threshold classifiers and not using our algorithm, they're just doing this fitting step and not trying anything more clever than that, then what happens is the seller uses a strategy which forces the buyer to trade off errors. They can either not buy when they should buy, or they can buy when they shouldn't buy. Okay, and what this argument which was first in Rubinstein, kind of shows that if you're clever, you can ensure that the loss in the middle is larger than the loss at the extreme. Okay, and in particular, you can be at this extreme with very high probability. Okay, so that's where this exploitation is coming from. Okay, so if all we could do was fit single threshold classifiers, then we would be in trouble. We wouldn't be able to get rationality, and that's something that the seller would in fact want to exploit, and then we would see a different data generating process. So now let me tell you our algorithm, and this is, I think, what JC was, I think, yeah, I'll be able to kind of explicitly answer this question more here. So at each step, so first of all, we initialize with some distribution over prices, which we're just going to take to be this uniform over the support of the strategy space. Okay, and so this massaging that I'm talking about in reference to Jingtao's question is essentially discretizing this seller's strategy space. Okay, so at each step, you start with a distribution, say DT, and then you choose HT to solve this optimization problem I had before. So remember, this is something the algorithm is able to do. Okay, and the output, as I said, is going to be look at stage T. It's going to look at the convex combination of all the classifiers that have been fit up until that point, take this combination of them, and then recommend buy if it's positive and not buy if it's negative. Okay. And so, in order to find, so this has this recursive form. There's lots of nice things about it. So you might, think this is really great. The part that's maybe a little bit more magical is finding these weights, alphas, as well as how we update the distribution. So let me say a little bit about this, because I think it might be not, so clear if you're kind of looking at it. So, the first thing I want you to realize is that if you were making a random guess, then this epsilon t would be equal to 1/2. You would be wrong half the time if you're kind of flipping a coin. So, if you're doing very, very badly, then you look at this, what the weight is, and this weight alpha t is going to be 0. Log of 1 and log of 1 is 0. So you're not going to be putting any weight on classifiers that do very badly. And as epsilon is going to 1, as you're getting very, very, as epsilon is going to 0, you're getting very, very good fits. Then the weight on the classifier is going to go, on that particular classifier is going to, go to infinity. So what this algorithm is doing is choosing these weights to put lots of emphasis on the classifiers that do well, and less emphasis on the classifiers that don't do well. Okay, but what about these distributions? How does it update these things? Well, remember that if y is equal to h, and both of those are 1, okay, then you made the correct classification. In that case, that observation is weighted less. Okay, so if a price is weighted, is correctly fitted, is fit correctly, we kind of worry about that price a little bit less. But if it's incorrectly fitted, then this is, y times h is -1. So this is exp of a number, exp of a positive number. And so that distribution gets more weight. Okay, so what we're doing with these distributions is, putting more emphasis on prices that are incorrectly satisfied, less weight on incorrectly classified, less weight on those that are correctly classified. Okay, so that's the kind of, I think, intuition for why this why or how this algorithm is working. It shouldn't be at all obvious that this works, but that's the intuition.
Hi, Johnson. Hi.
Yeah.
Quick. I want to clarify on the algorithm in the previous slide.
Mm-hmm.
Can you? Oh, yeah. So I'm slightly confused. So this T, this subscript T, has nothing to do with period, right? This is just the steps of this iteration.
That's right. Yeah. So yeah, you're exactly right. So
so D1T is taken according to the strategy. So D1P is given, then you try to iterate and improve the distribution over
yes,
the
that's exactly right. So the algorithm, the algorithm designer, if you would like, decides how many times to do this. It's not time. It's not calendar time. It's times you.
Right.
We should probably use an S or something.
Then this T, this is the exogenous choice of the algorithm, or is there like a stopping threshold?
Yeah, it's something that we're gonna take. Yes, it's a choice of the algorithm.
That is chosen in period 0 or period -1.
So what I want you to think about is it doesn't take any time to run this algorithm. Okay, running the algorithm is very quick.
Right.
And so in particular, as this game goes on and on, we're going to have lots and lots of data. Okay, and so the data is going to be getting large. And we'll also be able to, fit more and more, to run this for more and more iterations. So I want you to think of the data, the amount of data, and the number of iterations as kind of distinct. Does that make sense?
Sorry, maybe I didn't communicate well what I want to ask. So I was trying to understand what is this T, right? So your final output is the capital HT, which is basically a combination of all that HKP. So this number H1 up to HT. So how is this T decided? Is this T a choice at period -1, or this T is generated due to some stopping condition? Does that make sense? Or
in other words, is T endogenous to the algorithm, or is T pre-specified? I think
it's
right way to think about it.
It's endogenous to the algorithm. Yeah, it's chosen by the algorithm designer.
At period -1?
At period well, so what I'm trying to say is it's chosen at period -1, but but as time goes on and on, like calendar time, as more and more buyers arrive, they can choose better and better, choose higher and higher.
So in other words, there is no guarantee that this recursive problem will convert, and that's why you have to fix a pre-specified T.
Yeah, I mean, we have to like give a prediction eventually, and we have to tell, eventually we're going to have to tell the buyer what to do. So there has to be some kind of final time. Okay. And that's something that has to be, specified in advance. Okay. But what I'm trying to emphasize is it can depend on how much, how much data you have.
Okay.
Can I jump in the discussion here?
Yes.
Yeah.
Okay. The question about the endogeneity of T. You can interpret this T in 2 different ways. So if you are from the computer science, you can view this T as a training time. And you can choose a training time as a function of the delta rho. What is these 2 parameters? If you look at the definition of PAC learning, there are 2 parameters: epsilon accuracy and there is a
delta, yeah.
Delta, the
reliability
two error.
row. Yeah. So if you give me row, then I can choose T. So in that sense, this training period is part of the algorithmic choice.
I see.
Oh, got it. That's very clear.
Give me reliability, then I'll choose T.
Yeah, thank you. That's super
if you're
clear
coming
now.
from the repeated game type people, and if you can think this as a kind of ongoing process, the uniform convergence, if there is a convergence property there, so it's a uniform convergence will guarantee that within uniform number of rounds, this big HT will give you a correct answer within that bound.
Got it. Yeah.
Thank
you.
Yeah, thanks. Good. So, you know, the thing to emphasize is that except for this fitting, we just have algebra. Okay, finding these weights and distributions is just an algebraic calculation. And our result is that modulo this, how you decide to kind of discretize the price space, we have this algorithm is going to work. It's going to lead to consistent estimation in this, you know, we have this, you know, PAC-Learnability condition satisfied. And the seller in particular is going to be using, you know, the strategy they would use if the buyer were rational. Okay. And so, you know, in the proof, so I'm going to do a sketch of the proof in maybe, I think 10-ish minutes. You know, but so in the, you know, in the paper, we think a lot about like, what are these rates and how well does it do? So there's, you know, two broad sections to the analysis. So the first is showing that given a particular sigma, appropriately restricted, this algorithm is going to, in fact, deliver rational replies. This we're going to borrow heavily from this machine learning literature. And then the second step of the proof is to show that, you know, provided the buyer has access to this AdaBoost algorithm, in fact, these are the sigmas that are going to be emerging as optimal. Okay, so that's sort of the helicopter picture of how this analysis goes. The first part is this statistical part, and then the second part is where we think about the incentives. So the condition you need for AdaBoost to, you know, you know, give an exponential rate of convergence is this weak learnability condition. Okay, so you'll remember I said that if you're kind of flipping a coin and guessing randomly, then this objective would be equal to 0. If you got it completely right, it would be equal to 1. Okay, but if you were just guessing, it would be 0. So the condition for AdaBoost to work is that you can do better than just this coin flip. Okay. So you don't have to get all the way to 1. So getting all the way to 1 would mean you've got it right completely. You only need to get, you know, rather than get all the way to 1, you need to get slightly above 0. But the trick is that this slightly above 0 has to hold for all distributions D. Okay. And so that's kind of the hard part of weak learnability. Is making sure this is true for all D. So to apply this algorithm, we need to have you know, the weak learnability holding on our hypothesis class. And the issue is that if we have certain very messy seller strategies, then you know, then we run into trouble. So if you look at strategies of the form where the seller kind of alternates very aggressively between having prices at which the buyer should buy versus not buy. Okay, in that case, the how much better than random guessing you do is 1 over the number of prices in the support. So, and you remember that's exactly the adding prices to the support is how the seller exploits the buyer. So in the paper, we have 2 options. And so this is kind of this massaging I was telling about. The first is kind of grouping the prices into buckets, appropriately chosen, and then letting these buckets get smaller and smaller. And then the second is smoothing out the seller strategy by adding kind of small bits of noise to the price. Essentially doing the same thing, because adding the small bits of noise kind of ensures that the same action would want to be taken in in a kind of small bucket. Okay, the second part of the proof, and I'll try to go through these last points pretty quickly because I'm a little over time. The second part is kind of dealing with this problem of ensuring that we have the correct label. So you'll remember that we see the ex post observable, the ex post optimal decision. So we observe the theta ex post. And so we need to kind of estimate, what would a rational buyer who also can't see the theta, what would they do? Okay. And so for that, we take an empirical average, and use the fact that when we have a lot of data, all of these different prices are going to be, all of these different labels are going to be estimated uniformly well. And so this uniformity is kind of the hard part, and we appeal to Kramer's theorem to kind of to show that as long as there's a gap between the expected value and the price, we get our exponential convergence here. Okay, and so these results together show that we can, for these particular strategies, we can get arbitrarily close to rationality. And so the last step is just to verify that as long as we can do that, the seller doesn't want to deviate and fool the buyer in some other way. Okay, and this, we use this kind of undiscounted limit again to kind of show that any gains would be short-lived. Good. So that was a bit quick, but hopefully it at least gives a flavor, for how this analysis looks. And so the big takeaways are that fitting single threshold classifiers by itself, that can be exploited. The seller would be able to exploit the limited rationality of the buyer to do even better. But what this algorithm design lets us do is, combine these classifiers so that even though you can only fit restricted models, if you're able to combine the classifiers, you can, you can get rational behavior. So that's what I have for today. What we did was, propose a machine learning algorithm as a solution to a theoretical model, solving, reflecting some kind of bounded rationality, which features this interaction between the data generating process and the algorithm design question. Yeah. So, again, I'm running out of time. Let me just end on a few comments about next steps. I think, I want to say we do have some additional results. So we've been thinking of, we can in particular handle more than 2 actions. So it's not so important, it turns out, that the buyer just has the recommendation buy or not buy. You could also add a quality component there if you would like. Although you would have to maybe specify a slightly different hypothesis space. But we can again show this weak learnability condition can be satisfied under some appropriate, similar steps to what I described. So, I think in terms of next steps, I think, one area to think about is how to accommodate other concerns, or what kind of other concerns that people might have with these algorithms could be accommodated, and when might you worry about them in these in models like the ones we developed. So in particular, if you have concerns about overfitting, that's something machine learning people think about a lot. One question you might be interested in is why, under what conditions should you worry about overfitting? Okay, and so I think the second thing I want to say is that I think there's a big research agenda here that other fields have been following, which is to kind of try to open up the black box of these algorithms. So there's so I have a reference here to a statistical physics paper where they try to figure out in particular applications, why does one algorithm outperform another? A lot of these a lot of times in the machine learning literature, it's more vague as to why you would prefer one over the other. And so one kind of area I think theorists could be potentially contribute is trying to understand when do these algorithms work or not, or what are the properties that are kind of inside of this black box. But I think if you look at the growth in this area, I think it's likely to be an exciting area in the future. So I'm a little bit over time, but I guess we have 7 minutes for any questions.
Alex again. So I think when you started, the part of the pitch was to say, well, look, I'm gonna look at bounded rationality versus incentives. First one being tractable, second one is intractable, and I'm gonna give you the best possible solution. And the solution is now clear and is super nice, but in some sense I was thinking this is going to be something like necessary and sufficient, so I can kind of understand why this works, but how do we know there's nothing that works better? Is there any way in which, perhaps in the paper but not in the talk, you compare what you guys are doing either with other things and explain why this is better? Or is there any sense in which if I do this, I know I can't do better?
That's a good question. I don't entirely know how to address it without kind of creating a straw man. One thing I can say is that these weights that we picked are a little bit ad hoc, actually, in the sense that other versions of the same algorithm specify the weights in kind of slightly different ways. So I mean, it works for our proofs, right? So it's not ad hoc in that sense. but if you look at, in this kind of literature studying these algorithms, there's actually kind of there are potentially other weights you could use. If you look at where it comes from, it comes from kind of minimizing. So what you do is you kind of bound the loss function by an exponential. Okay, that's sort of how this proof works. And the point is that the exponential is kind of is smooth, whereas this like kind of step function for the loss is kind of not. And so if you use different kind of bounding functions, then you would get different, slightly different weights. And I don't think there's too much, as far as I know of, you could be very clever with finding another, another way of specifying the weights potentially. So that's sort of what I'm trying to say, and I'm not sure if that would necessarily break. I don't know if Inku had anything to add, but that would be my short answer. But it's an interesting question about like what other algorithms could you look at.
I was just thinking that there's various ways. For instance, you can compare algorithms by their degree of manipulability. For instance, in matching theory, you can show that something is, if I want to compare two algorithms, I could say, well, one is manipulable every single time, the other one is too, and that gives you a concrete way to compare them. But I get the point, and thank you.
No, it's yeah, it's a good question. It would be good if we had a kind of really precise way.
We just showed the possibility. We just showed that there is one algorithm which
exactly
such that bounded rational guy can emulate rational guy.
Yeah.
We have not tried to show it is the algorithm that far. So this is where we are now. Your point is well taken. Thank you.
Any other question for Jonathan?
Yeah, and obviously email is also, if anyone has, happy to get emails from you guys.
Well, we can clearly see the addresses, right. and I think it's a good time to just say thank you once again. We appreciate this is not the easiest time for you to give a talk, so thank you once again.
No, it's really a lot of fun.
So let's end the session. Thanks Jonathan again, and I hope to see you next week with what, the 5th session or something like that. Hopefully I'll see you next week. Bye-bye.
Bye.